to #physics with Mr. Elliott. Today I'm going to go over the electric force number line problem, just so you have an idea of how to work through a 3-charge problem that are all in the horizontal plane on the x-axis. This is a problem in your notebooks. So, problem looks like this. What we're asking you to do is to, in the end goal is to find the net force on each one of these 3 charges. The problem states a positive charge of 25 microcoulombs is located at point x1 equals -8 meters. A negative charge, q2 equals -10 microcoulombs, is located at point x2 equals 0 meters. And a positive charge, q3 equals 15 microcoulombs, is located at point x equals 4 meters. Draw a free body diagram for each one. We need the free body diagram in order to later add up the forces with the correct sign. Everything going to the left will be negative, everything going to the right will be positive. So, I need to look at these 3 and see the interactions to determine what direction the electric force will go. I know this one is positive, I know this one is negative, and this one is also positive. So I start by drawing a dot, represents Q1, and I'm going to draw the direction of the forces. I'm going to do this in red. So if I look Q1 and Q2, those two are attracted to each other because opposite charges attract. So I have 25 microcoulombs, that's positive. -10, they will attract to each other. So I can put another dot for Q2 here. And I can draw a force on each one going towards the other. Other thing I have to do is label this force for later on. I'm going to label this one as F21, the force, F12, the force on object 1 from object 2, F12. The second one is F21. Now I just have to do this 2 more times between the 2 other objects. So I look at Q1 and Q3, for instance. I see Q1 is positive, Q3 is positive, they repel. So I'll draw that one in blue. This one will be F13. This one, F31. Now those 2 forces will be equal but opposite directions. Same with these 2 red forces. Equal but opposite directions. Our last interaction, Q2 and Q3. Do they attract? Do they repel? Q2 is negative, Q3 is positive, meaning they attract. Therefore, I draw a force for each one towards the other. This one I'm going to label as F23 and F32. I want to reiterate this one more time. Red forces are equal in magnitude, opposite direction. Blue forces equal in magnitude, opposite direction. Same with the green forces, because they're the same charges in the equation that we're going to use. So that's our free body diagram. We're going to come back to this at the end. First, we have to find what are the numbers for these forces before we can get the total net force. And that's where we get to parts B, C, and D. Parts B, C, and D. Part B. Find the magnitude of the force between Q1 and Q2. Well, let's write down our givens, right? We know we're given Q1 equals 25 microcoulombs. To get rid of that micro, or that mu, I do times 10 to the -6. So it's 25 times 10 to the -6 coulomb. Because in our equation, we need it to be in simple coulombs, not microcoulombs. Q2, same thing, except it's 10 microcoulombs. Our radius between the 2, which is going to be important. You have 1, 2, 3, 4, 5, 6, 7, 8. Radius is going to be 8 meters. In our equation, what equation are we going to use? Well, this is the electric force. It's proportional to the two charges that we have and inversely proportional to the radius squared. It becomes K, which is our constant, Q1, Q2, the absolute values of those, which is why I didn't put the negative on this, -10, divided by the radius squared. You should never get a negative number for the magnitude of FE, because these two are absolute values. And your radius can never be negative, it's just a distance. So, FE equals K, which is 9 times 10 to the 9th, times Q1, which would come back over here, 25 times 10 to the -6, times 10 times 10 to the -6, divided by 8 squared. I'll give you a minute to take a look at that and review it, and we'll get our answer. And our answer here becomes 0.035 newtons. Okay? 0.035 newtons is our electric force between Q1 and Q2. So that's equal to F12 and F21, 0.035 with direction permitting, positive or negative. Part C, same question, but for Q1 and Q3. Well, I know as Q3 is 15, so let me write that one over here. Again, times 10 to the -6. We're going to go to part C. The radius between those two, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or I could have just done 8 plus 4. So our radius here, 12 meters. We're going to use the same equation. Q1, Q3 this time, divided by R squared. FE equals 9 times 10 to the 9th times, go back to Q1, 25 times 10 to the -6 times Q3, 15 times 10 to the -6 divided by 12 squared. Give you a minute to take that down. Our answer, rounded, for F13 and F31, because it's the force between Q1 and Q3, becomes 0.023 newtons. That's our answer for F13 and F31. Our answer for part C. Part D. Just the last two, Q2 and Q3. We have both givens already. We can just plug it in. We know FE is equal to K, Q2, Q3 this time, divided by the radius squared. We need to know what that radius is. It's from 0 to 4. Our radius is 4 meters. We use the same givens as before. FE equals 9 times 10 to the 9th times Q2, 10 times 10 to the -6, positive because it's absolute value, times Q3, 15 times 10 to the -6, divided by our radius, which is 4 squared. Our answer for this one, is F23 and F32 equals 0.084 rounded newtons. So we have our 3. Force between 1 and 2, force between 1 and 3, force between 2 and 3. And now, we need to find the net force. So we go back to our free body diagrams, and we look at each one. And on our free body diagrams, we're going to use that to find what's negative. So let's write that one down on the whiteboard here. So if I write for Q1, I had F13 and F12. So when I look at that, that tells me that F13 will be negative. So when it asks us for part E, find the magnitude and direction of the net force. I use my free body diagram to get my answer here. So I look here, because it's going to the left, that's negative. Because that's going to the right, that's positive. So I write it as F12 minus F13. That's equal to, going back, F12 is in red, 0.035 minus 0.023. So, our net force on charge 1 is equal to 0.012 newtons. And it's a positive number, meaning it's going to be to the right. Let's go back. For Q2, we need to look at our free body diagram here. That just changes our forces. We have F21 and we have F23. So for part F, the net force on object 2, I look here again, I have F21 is negative, so I do F23 minus F21. When I put that back in, I look here, that will be 0.084 minus 0.023. That means our net force on object 2 is going to be 0.061 to the right, because it's positive. And the last one, part G. Sometimes we forget our alphabet. We go back, we look here. Instead, I have F32 and I have F31. So that's what our free body diagram is going to look like. We look here. F31 is 0.023. F32 is 0.084. So, I look here. The net force on object 3 equals, again, F31 minus F32 which was 0.023 minus 0.084, that's equal to 0.061. And that's to the left. Now bringing this up tells me this one must be incorrect. What did I do incorrectly? Well, if I see here F21, if I go back, F21 is not 0.023, it's 0.035. So I have to make that correction here. And that changes it. We now have 0.049 newtons to the right from that force on 2. Notice, as I'm continually going along, I'm checking my answers. You may have noticed as I did it that I put the wrong number in there, but that's what happens when you go a little fast. You want to always make sure you're going back. I caught it before I finished up. Scientists, we make mistakes all the time, but we always, always, always check our work and strive to get better. All right? This is how you solve for the net force. This is our final product for each one of these on these objects. In other words, if I released all three at the same time from rest, object 1 would be moving to the right, object 2 would move to the right, and object 3 would move to the left. So you'd think at some point these two might collide into each other. But obviously, they're going to start to change their forces as they move closer and farther away from each other. All right? So, that is electric force number line question. Stay tuned for more. I'm going to do a little bit more of our electric force, especially some demonstrations about induction and conduction. Thanks.